Welcome to Dr. Jimmy's Applied Calculus, ready for Section 6.5. Topic of related rates. So let's see, we have two words there. Let's look at the word rate. This is looking at changes relative to time. So we get those in a few places that we might notice. Interest rate is a rate. Interest rate is the change in amount. So how much do you have in maybe a savings account? So it's the change in the amount over time. So a certain amount added to the original amount given the amount of time. Another place that people might notice is that speed is actually a rate. It's the change in, well, how far you go over a fixed amount of time, like 50 miles in 1 hour is a speed. So that would be known generically as a rate. Anything compared to time, the change over change in time, is a rate. So if we have something, a function of t, now in most cases when we use the variable t will mean time. So as a function of time, more specifically than some generic variable x or something else, then this would be the change in y over the change in time as a rate. Of course, that would be for fixed non-dynamic situations. When the dynamic situation, it's the limit of those creatures, and so a rate is the derivative in terms of time, or in the same notation, the derivative of f in terms of time. We also have dy dt, exactly the same thing, or maybe df dt. So we could use any of those, but they all come down to the derivative, but with respect to time, as opposed to other possible variables. So rate is just a slope, it's a derivative, it's a change with respect to a variable, but in more specific, it's in terms of time. So that's the word rate. Now, we're looking at related rates. So let's look at this setting. We have a price, P in dollars. We have commodity available. So there's a certain amount of quantity units of something available, such as we might think of barrels of oil, something such as that. And so we get this relationship between those two items. So we have a relationship p squared times q cubed equals 6 million plus 100 q exponent 2.5. So this relates the two variables p and q. It's a relationship. It's a set of ordered pairs. So there we get relationship. So we have rate and we have a relationship, or something that relates to things. So this might be somewhat indicative of things. Notice that this model, as the quantity available increases, the price drops. Sort of like if there are more barrels of oil available, the price goes down. If the quantity gets less or decreases, we notice then the price goes up. So not an unusual type of model for quantity available and price. Now, we talked about rates have to do with time. Here's a relationship, but in this relationship, time is not mentioned, nor is time in the graph. So out there in the real world, you would have different times. So you would look at, maybe right now, we're at this point on the graph. We might look, say, a month later, and we're at a different point. So the price has changed and the quantity. They both change according to that graph. Maybe if we look a month after that, we see another place. So everything changes. Look again in a month. So over time, you move to different points on this graph. So in that way, T is involved, but it's implicit. So we have the basic curve, P and Q. But if we look at this from the perspective of time, at different points in time, we'll be at different points on the graph. So in the background somewhere, time is involved. It becomes P and Q depend on time. So we don't know what those functions of time are, but then we know that if we look at any point in time, we'll be somewhere on the curve. So we have a relationship, time not mentioned, but then we ask questions according to time relative to the picture. So we have a relationship here. And a point on the curve is when the commodity units available are 100, the price is 4 in the graph. When the commodity units are 1,000, then the price is approximately 1.78. So in terms of dollars, we would have, if we only have 100 units available, the price is moved up to $4, but if we have a lot more, like 1,000, we get approximately $1.78. So we could come up with different points on the curve, possibly. So by substituting P's and Q's, solving for the other one. So it might just be, here's a point on the curve. Now, we end up having other questions relative to this situation. We might ask something like, how fast is the price changing? When the quantity is dropping at 5 units per day. So in this question, what do we have? We're looking at a trend in the quantity. So it looks like we're going to be, the quantity is going down at 5 units per day. So we're given the 5 units per day is relative to the rate of the quantity. How is it changing? A change of quantity per amount of time. And it said it was dropping, so the change is actually negative. So that's the part here. Quantity dropping at 5 units per day is actually a rate. How fast does it change in time? We're asked to find how fast the price changes. So that's the rate of change of the price. So now we're asking questions about not just P and Q, but their rates. Now, we don't have Q of T and P of T explicit, but only implicitly in our relationship equation. So our T squared Q cubed equals 6 million plus 100Q exponent 2.5. So from that relation, we can find derivatives. So we'll take the derivative in terms of time of the expression on the left side and also do that on the right side. So with derivatives, those should end up equal. So we go back to implicit differentiation, but the derivative here is not in terms of either of the two variables appearing P or Q, but we still use our derivative rules. So the left side is a product. So we'll have P squared and the derivative in terms of time of the other factor, Q cubed, plus Now q cubed with the derivative of the other factor p squared. On the right side, I have the derivative of a constant plus 100 and the derivative of q with the power exponent 2.5. So that would be 2.5, the variable, subtract 1, and we would have an exponent of 1.5. But this is a derivative in terms of t, which doesn't match q, so there's always, at the finish, one extra factor. That's the derivative of the symbol. So in this case, dq dt. So that comes out of the chain rule. And so working a little further, we have p squared, we have the derivative of q squared, 3q squared, but again dq dt, because it's in terms of time, as a factor from the chain rule. And then we get q cubed, derivative of p squared, 2p, and again all the way to t. Chain rule says we need a factor, the derivative of p. So that would be the left side, the right side. Let's see, we can write that as 250 q with an exponent 1.5 and then the derivative of q. So we were given information about the derivative of q directly. So let's take this equation. We want to know something about how does p change over time, its rate. So if I solved, I would subtract this dq dt term, left and right. When I was done, then I could divide by the coefficient of the dp dt. So I just did that because I have this equation which relates the rates of the variables now. So related rates in this. So we start with a relationship, I turn it into a relationship of the rates. Now I have information about how q changes. I'm trying to find how p changes. So I might solve it in this form. I wouldn't have to yet. Now we had the change in q over time at the current rate is -5, dropping 5 units a day. This may change in the future, but for the moment, we're saying that's what we have. So that would give us the change or the rate of change in the price. Well, we're not going to quite get a unique answer here. We're going to get 250 q exponent 1.5 then -5 -3 p squared q cubed -5 for the change in q again over 2p q cubed. So the change in price, it also will depend on what's happening at the moment. At what point PQ or QP are we on that curve? So we need more information to be give a specific change in price. And so there was a point on the curve. If Q is 100, P is 4. So if that was our current state, then we could come up with a particular rate of change of the price. So now I'm just substituting Q's with 100 and P. Every time I see a P, substitute a 4. And I think I copied, I noticed this below. One of the exponents, this would be P squared Q squared somewhere. Not P squared Q cubed. Okay. So we get a change in the price. So if I work this out a little bit, let's see what we get. The half power of 100, that's just the square root, that would be 10. And this is 3 halves, so this is 10 cubed. And we have a minus 5. And this one is a plus. Three, 5, we get 4 squared. And 100 squared. So I'm looking at all the tens going on here. So if I factor out a 2 from 250, that makes another 10. So I could write that 125 10 to the 4th here in the front. Plus 3. If I take one of the 2's from 4 squared, that will leave 8, and another 10 here. And this is actually 10 to the 4th. And this would be 10 to the 6th if I turned it into tens. So, going along without a calculator, if I fiddle with tens, not too bad. So if I divide through or by 10 to the fourth, I end up at this next step because I cancel every power 10 to the fourth. It would leave 1 here, none there, and 2 on the bottom, which is 100. So I get 240 minus 125, so 115 over 800. So we could reduce that a little, but we see the price is going up a certain amount per day. So part of $1, close to an eighth or maybe a sixth of $1 a day. So related rates. We start with a setting where we have a relationship between values, in this case P and Q. No T mentioned, but in the real setting, they usually both depend on time. They both change as time changes. So it's implicitly embedded here, P of T and Q of T. So we can take that relationship find derivatives in time. So that's done in this implicit fashion. Derivative of left and right, all in terms of T. Whenever we get down finally to just the variable Q or P, we have a final derivative factor, derivative of Q in time, and derivative in P in time. So that sets up a relationship between the rates. And then we can answer questions based upon how things are changing in time and where we are at that particular